So today I'm going to quickly talk about just a paper that I've read. Didn't have a lot of results to present about the quantum battery at the moment, so I decided to choose a paper to discuss. And this paper is from enhanced diffusion of ultrafast ballistic motion in polariton devices, so light matter coupling. And this was released start of this year, or published start of this year.
It's 2022.
Published online 16, 2020.
Oh, 2023 last year.
So it's fairly close for now.
And Jonathan Keeling wrote the foreword to it, you know, like the fluff piece.
Oh, right, okay.
Yeah, because I thought it looked familiar. He called it, the fluff piece is called See How They Run, like Three Blind Mice.
Oh, okay.
It's funny.
Right.
Anyway.
How was it? How's the piece?
Yeah, it's all right. So made me want to read this paper.
So just a quick overview. This paper is really about transport properties when you have a light matter coupled system, and I'll give a basic overview of that in a second. But what they find is that there's this interplay between diffusive molecular transport and ballistic transport, which is inherited from the light matter coupling. And what they show is a 10 to the 6 increase in diffusion length of their light matter coupled quasi-particles compared to the bare matter system. And then they also show that they have ballistic transport, which is transport in a system without scattering. And that's and they show that for a 20% matter polariton, which is quite remarkable, I think. This sort of physics, like the ballistic transport, is fairly relevant for photovoltaic applications like the quantum battery, quantum OLED, and any sort of light harvesting where you want to turn a photon into electrical energy and you want to transport this over some distance. So just a reminder of polaritons for anyone who's forgotten. Basically, we couple a quantized cavity mode to molecular excitation, and you have your polaritons, and this fundamentally changes your sample due to this hybridization. So on the left, we have dispersion relation of all the, where's my laser? Of our various components of polariton. So an exciton, which is a molecular excitation, is the red line, and the photon, which is the cavity mode, is the blue line. And you see the photon has some in-plane momentum dependence, so that's like an angle dependence, whereas the exciton doesn't have that. So when they couple together, you hybridize and you get polariton branches, which are distinctly different from your bare exciton and photon. And here's just a kind of a simple plot of what this would look like in reflection measurement. So in the blue is just the bare cavity, which is just the confined photons to some structure. The orange here is some molecular absorption, which is decreasing this reflection. And then when they're hybridized together, you get your polaritons, which is the green one. And you can see that it's shifted from either of these peaks, and it's some combination of both of them. So it can't be explained by either of them separately. All right, so that's polaritons. That's polaritons based on a cavity system. In this paper, they look at block surface wave polaritons. So in this scheme, they don't have a cavity, but they have a DBR, which is a bunch of alternating refractive indexes. And ultimately, this periodic structure gives rise to interference between incoming light, and it can form a standing wave, similar to a cavity structure. And this standing wave can then be coupled to some molecular absorption or excitation, and you get your polaritons that way. So they've got a similar dispersion relation here, where you've got your white line here is the excitonic relation, and this block surface wave is this diagonal line here. And then they've got their lower polariton block surface wave here, and you can extract your Rabi splitting from this plot as well. For this case, they have it as 142 MeV, which is somewhat comparable to what we have in our quantum battery devices. And then on the right here, they show the diffusion of this polariton, lower polariton, as a function of its mixing. So you can have your excitonic weight and your photon weight of your polariton, and this is just varying the photon weight. So 90% photon is here with 10% exciton. And they show as you increase the photonic weight, it moves, it diffuses further.
How do they do that? How they?
I don't have the picture of it, but they have it's a pump probe setup, and they use like a plate to vary the position of the probe, so they can measure the spatial location of where the probe's hitting. And since they've got the pump probe set up, they can do this as a function of time as well. So they can see spatial and spectral information as you move your probe beam.
No, I mean, how do they change APH, the number of photons?
So you can do that by detuning from your polariton energy. So I think they do a broadband pump of everything, and then they choose a very specific probe energy to directly probe certain polariton energies with a very well-defined wave vector. So they can probe like a vertical line here if they control the angle of their probe. So yeah, they can probe their different polariton wave vectors. So one question you might ask is, why would we use this block surface wave polariton over a cavity polariton? And it's basically because you can get longer cavity lifetimes and larger propagation distances. So on the left, we've got our regular cavity polariton setup we've shown, and then they've plotted here the velocity of, I think the maximum velocity you can get in that sort of system. So this is on the order of 30 micrometers per picosecond, whereas in the block surface wave polariton, you can get hundreds of micrometers per picosecond. They also have a cavity lifetime on the order of 150 picoseconds, which is many orders of magnitude larger than what we have in our cavity devices.
Last question on this one.
Yep.
Why is it that the velocities go down as the energy goes up? Is there an obvious?
Like here and here.
Yeah.
Yeah, I'm not entirely sure about that one. I'd have to get back to you.
I think the group velocity is like, I think this is a derivative of the energy spectrum, I think. The effect, I don't remember. So, so for photon, E equals PC. So P is like the velocity. So P is P is equal to E on C. And the velocity is, so P is like mv, so V is E on M. There's no mass in a photon, so it's E decays.
Because yeah, I think isn't P related? So P comes from the Broglie
That's right.
relation, right?
Yes, use that one. Yeah.
So then
P equals H bar K. So then E, so it's K. Yes, so the E decays. So you take the derivative of the blue line, you get the bottom line.
Okay.
Not sure how they did it, but that's theoretically it'd be DEDK.
Yeah, they don't have a caption. So moving on to one of their first measurements, which is and here's what the kind of setup looks like, is their ultrafast spatially resolved signal, which essentially shows your polaritons, or a polariton cloud, as they describe it, evolving in time, and this is at a 1 picosecond time frame. So it is very fast, and you can see that the signal extends out to hundreds of micrometers in less than a picosecond. So this is a propagation distance, which is an order of magnitude faster than cavities, Fabry-Perot cavities, like what we use. And the expansion is, the velocity is 2 orders of magnitude faster.
Is this optical?
What do you mean?
The light operating wavelength?
Yeah. So this is around 580 nanometers.
Right, okay, so it goes quite far. So nano is 10 to the -9 micros, so 3 orders of magnitude. Like it moves 1,000 times its wavelength, 1 picosecond.
So it is incredibly fast, and this is for a polariton with photonic weight of 0.82, so it's fairly photonic. Another way of looking at this plot is to kind of take slices of it, and now they compare different photonic fractions. So in this case here, they have 0 photon weight, or the bare molecules, and they increase it like that. And for the 0 case, the bare molecules, you can see it doesn't change its width at all. So the diffusion is basically non-existent because they can't measure that small. So it stays around 6 microns the whole way. But as you start to increase the photonic fraction, eventually you get to such a large diffusion that it's considered ballistic transport, where this is this diffusion length is larger than the area that they're looking at. And so then they have a really nice looking plot, in my opinion, is they show these like diffusion, what's this, the diffusion time versus the I think the amplitude, and they can identify a bunch of different regimes. So these are all the different photonic fractions, and they can identify regimes that it would be ballistic and if it was diffusive. So this, the black lines here are ballistic transport, and that comes out from their theory. And the red lines are diffusive transport. So this diffusive transport would be more molecular in origin, and the ballistic is arising because of this light matter coupling. And what's very interesting is there's kind of a crossover regime between ballistic transport and diffusive transport at some point, and this point is kind of governed by the sample properties. And yeah, this is just a plot showing that the black lines all fall on this this 2 value here, which means it's ballistic transport, and the 1 value means it's diffusive transport.
Did they talk about dispersive transport?
The diffusive transport is
No, dispersive. What's the difference between ballistic and dispersive?
ballistic and diffusive.
No, dispersive.
Dispersive.
They talk about that.
So I think ballistic and dispersive. Dispersive transport is just like a photon photon transport through a material, I think. And ballistic transport is the
So as I recall, dispersive transport is scales as T, diffusive scales as square root of T, and what's ballistic?
ballistic transport is like a particle that is not a photon, but it's traveling without scattering.
Yeah, that's dispersive.
I think it might be called ballistic if it's a particle.
It's a particle, yeah.
Yeah.
Right. Okay.
Because is the difference between dispersive and diffusive just wave equation versus heat equation?
Well, diffusive normally has disorder or scattering, so that will scale the square root of T.
Yeah. Okay.
Yeah, and dispersive is a homogeneous medium. There's no scattering.
Because so when you solve in general the heat equation, I think, then you always have a square root T dependence with the diffusion coefficient in the exponents. Whereas in the wave equation, I think you always get T in the, so it's just T as the sinusoidal. Pretty sure.
Yeah.
I seem to remember.
So maybe ballistic is just dispersive, but yeah, for particles.
Yeah. So when ballistic transport occurs when you don't have diffusive, there's no diffusion.
Because they say like in the Landauer formula for a current, that's ballistic transport because you don't take into account electron-electron interactions or anything. You just assume it goes straight. Yeah. So.
And is that wave-like or particle-like that?
It's wave-like.
Right. Okay.
Yeah.
So maybe ballistic is basically the same.
So this might help answer some questions. So this is what the 10 to the 6 enhancement. This is where it comes from. So this red line here comes from that previous plot of these red points here. That's the diffusion regime, and then the black one is the ballistic regime. So as you increase your photonic weight, you get larger and larger diffusion coefficient, and you don't go faster than the speed of light though. But at this point, you lose diffusion because it's reached the speed of light. And then from then on, it's ballistic transport. However, if the medium that they were looking at was perfectly homogeneous with perfect delocalized wave functions, they should follow this solid black line here. But what they observe is the dotted black line for their velocity. And this comes from some kinetic model with some polariton scattering which is thermally activated. And it fits fairly well, apart from this point. But this is pretty direct evidence of ballistic transport, I think, which is where your polaritons are moving without scattering. So sorry, this is where the 10 to the 6 enhancement comes from. So this diffusion coefficient that they get out of this plot, they compare it to regular semiconductors, and it's 10 to the -3 to 10 to the -7. So they're more than 6 orders of magnitude larger, which is a very large enhancement. So if we get kind of at the macroscopic properties from these kind of diffusion plots. So in semiconductors, your mean free path is on the order of a few nanometers or a nanometer, but in theirs it's hundreds of micrometers or tens of micrometers. And this is explained because the cavity enhances long-range spatial correlations because of its the polariton delocalized nature, but there's still underlying molecular disorder and dissipative processes, which mean the wave functions aren't perfect, they aren't infinitely delocalized. So they can say they can use this finite mean free path, which results of this disorder, to inform about the scattering mechanisms, or at least the values of the scattering mechanisms. They don't go into much detail of how these mechanisms act actually. So then in this plot, they see the mean free path increases as the scattering rate decreases as you increase the photon fraction. And just a point of comparison, this mean free path, so the path before there's some scattering event, is 4 orders of magnitude greater than the intermolecular spacing of their molecules, and that demonstrates this long-range correlation. So in conclusions for this paper, under the right conditions, light at a coupling can significantly enhance this transport of energy. They showed the 10 to the 6 increase when you have a 2080 matter photon polariton, and molecular disorder and long-range correlations can peak to give distinct transport properties. You have your diffusive regime and a ballistic regime. Ultimately, we want ballistic transport for photovoltaic applications because we want to shuttle photon energy into electrical as fast as possible with minimal losses. And in terms of relevance for us, while they kind of looked at disorder of polariton transport in this paper, they don't really explore the mechanisms of it, which is a ripe area for multidimensional coherent spectroscopy because it enables separation and identification of different mechanisms. You can separate the homogeneous and inhomogeneous broadening, and you can quantify interactions with photons and just generally interactions in general. So it could be useful to identify the different interactions, which how the disorder interacts with the polaritons as they transport. Another thing that could be important for us is ballistic transport of polaritons. It might be important for super extensive photocurrent, because if you imagine after superabsorption, if there'll be some sort of bottleneck if there's a dissipative processes where the polaritons aren't able to transport quickly enough to the leads. So perhaps we can construct some sort of device to exploit ballistic transport, which then brings up the idea of quantum batteries using block surface wave polaritons as an easier way to get ballistic transport. I'm not sure if we have ballistic transport in our current devices. I think, yeah, I don't think it transports ballistically, our polaritons. But it's something maybe we can figure out how to exploit, which maybe will enhance photocurrent, or maybe we can get a super extensive photocurrent if we can try and figure out some of this physics. And yeah, that's it.
Thank you. Questions, comments?
The paper look familiar?
Yeah, it does.
That's the one we were working on with Daniel Gomez for that grant application, which never.
Oh, that's right. Yes, yes. So it's Daniel. Yeah, Daniel's the one that sent it around.
No, I
You
sent
sent it around.
Yeah,
Okay.
yeah.
Yes.
So Daniel said that he'd worked on these kinds of devices before, but never to do electrical transport or anything.
Yeah.
But yeah, it was funny because
And you found it independently.
yeah, unprompted. I said, I know this.
I was looking for some sort of photocurrent, and even though this doesn't explicitly look at electrical measurements for photocurrent, I think it's still very relevant. It's like the prelude to photocurrent is the transport of polariton.
Yeah.
Well, so I actually had a comment on that part. So one thing that I found recently with trying to model these sorts of things is there's a big difference between a photocurrent and an exciton current, because where it's very easy to have enhancements of exciton currents with polaritons, because you can always translate a matter excitation into a photon, and the photon field then acts globally, and so can change into a matter excitation over here, and you've had the kind of ballistic transport. It's not so easy with an electrical current, because the electrical current, your excitation, so to speak, is the electron. And yeah, dissolving an electron into a photon, it's like a high order QED process, I think. So that's not to say that there aren't enhancements from electrical currents that come from these light matter interactions. And I have some models which show these enhanced currents by like teeny tiny bits, but I don't actually know what the mechanism is. I don't know why it works. I think it has something to do with changing the energy levels of the various molecules with respect to the work functions of the leads somehow, and that enhances the electron transport. But honestly, I don't actually know how that one works. And I think here what they're measuring is not an electrical enhancement, but is the excitonic enhancement. So they're seeing the polaritons propagate quickly. But anyway,
if you can break the excitons at the edges after they've done their transport, maybe that can.
But if you transport, so what you want to separate at the leads is an electron and a hole, right? If you create an excitation here, then you have electron hole bound pair, and you want the electron to go this way and the hole to go this way. But what we're talking about here, polariton movement, is more like moving this excitation here. So like I can imagine a kind of fret style process where you have electron excited, hole is here, and now the molecule next to it, he has the electron excited, and this one is that. And so this is an excitonic current, this is that one. But the charge current is when the electron and the hole hop their separate ways. And yeah, I mean, there's absolutely no reason why it can't be enhanced by light, but I think that the mechanism is much more subtle, and it's a super nice problem to try and attack. And you know, MDCS and these kinds of setups, I mean, it's a playground basically to do these kinds of experiments. So.
Can we? Is this useful for electrical current?
Could well be.
Yeah,
Yeah,
it
yeah.
might be.
So that's what I'm saying is, so that was actually the flavor of the grant application, was that, okay, they can do polyatonic transport very, very quickly, but what about electrical transport for a new generation of optoelectronic devices? And yeah, so like I said, I had that model of the quantum wire, which we showed Gabrielle, and there was like a region where you had a slightly enhanced current when there was a like a lat coupling. You could see it as a function of G, but I never actually got to understand why that was the case. It was just a numerical result.
So the initial current, it's the so it's the number of coulombs per second which passes through. This one is not the number of coulombs, right? Because the coulomb says the same. It's just that it's energy. Yeah. Okay. So the currency is important because the coulomb per second is also a measure of energy.
Well, so you generate electrical work, I guess, with the Coulomb. So you're ultimately transporting an electron given a voltage. So, you know, an electron with a voltage is an electron volt, which is still a unit of energy. But in this case, yeah, you're transporting an excitation, which then needs to be spent to do something else. Whereas with an electric current, it's just the electron passing through gives you the energy.
So is the idea then not to think about in the conventional classical electric current idea of the movement of energy, but in this one, whatever it is called, what shall we call it? Photocurrents.
Well, so the photocurrent is, so I mean, it has a meaning, which is the electrical. But I think in the literature they call these excitonic currents.
Excitonic currents.
And that's exactly what not Gabrielle, but Gabriel Hanna was talking about with his excitonic quantum battery. Because that one, the leads, so to speak, are excitonic reservoirs. So they're not putting electrons into the battery, but they're putting excitations, which are photons basically, whatever. So and yeah, I mean there's a study of excitonic currents.
Excitonic currents. So we know there's like a new type of engineering or physics. It's no longer like electric circuits. We're talking about exciton circuits, and instead of electrochemical potential for batteries, we're talking about sort of excitonic batteries, something like that. So the other thing is, so this is all about transport. Another thing we need to understand or try to work out is how to store the energy for a long time. How can we store? Because in the normal batteries, it's a chemical potential difference, which is thermodynamic in nature, right? And that is relatively. How do they make it stable?
Because there's a large activation barrier between the reactants and the products. So thermodynamically is kinetically is very stable, but thermodynamically it's metastable.
So what would be the equivalent for us for excitons? How do we
dark states?
One of dark states, the ones that we play with, they're not very stable in real life because with agitation, they're much stations in the go. So we need like really stable dark states. Maybe so at cold temperatures, I think that's okay. Maybe our stuff is only works at cold temperatures. But even then, like how long we're talking? We're not talking that long. These dark states, even at cold temperatures.
No, I don't think so.
Like how can we?
I mean the dominant mechanism for dark state relaxation is non-radiative incoherent relaxation, which usually is mediated by phonons. Right?
Exactly.
So if you cool everything down, then you basically remove all phonons from doing excitations, but it just means that the excitations then become possible, at least, so you can emit a phonon to a cold environment. There was some So in the single molecule magnet literature, they have exactly the same problem. They, and everything works at like 1 Kelvin best. There was some work on trying to engineer like really rigid lattices, so that it was even impossible to kind of emit phonons to the lattice, and you end up with this phonon bottleneck style effects, which artificially enhance the magnetic lifetime. So something like that potentially.
What's the order of magnitude in terms of how long stay for that?
With magnetic stuff, we're like microwaves, so they last for like microseconds, give or take. Here, because we're optical, picoseconds.
Then microseconds short, like if we want to have a like operating with like conventional circuitry, conventional.
There's this thing, I don't know a lot about it, I'll be honest, but it's called an excitonic insulator, which apparently can host excitons in the ground state in equilibrium. So it could be like a source or a storage for
So what's this called?
an excitonic insulator.
Oh, how long do they last for?
It's the ground state is an exciton.
Oh, okay. Okay. But even then, if it's in a closed system, right? An open system, it will just
In an open system at room temperature, apparently.
okay.
Yeah, I don't know a lot about it, but it might be. So this paper here was 2022.
Okay. Well, yeah.
It's maybe something to investigate.
Yeah, absolutely.
I'm not sure if it's
because I think if we solve this problem, then we could write a book. Right? Like excitonic circuits or whatever.
excitonic.
Excitonic something circuits.
Yeah.
Completely different type of, and they're no longer electrical, which is quite,
Would you have to have like some transduction mechanism so if I want to charge my computer with an excitonic current, then I don't know, do I need an adapter at some point to turn the energy stored in the excitonic current into
well,
electrical?
we need to if we want to work with a current grid, but we do that like we sort of do it now with the laser. Turns into laser and then an exciton. But the idea would replace the whole circuitry excitons instead of electrical.
Because what about if you stored energy still in like a thermodynamic, so it's still in the chemical reaction, but you just need to transduce that exciton into a chemical excitation. To fuel that charging process.
So that sort of makes sense for transport, but we're claiming we want a quantum battery. So we want the full thing. We want to replace the whole grid with quantum exciton power grid.
Yeah.
Okay, cool.